1, 2. All right, hello, and welcome to Thursday evening lecture. We are going to continue our discussion of acid-base chemistry. We're going to press deeper into the topic. Start looking at. We're going to start looking at different types of acid-base reactions. We are also going to see how acid-base chemistry connects to equilibria. So we have several really cool things lined up for today. But again, before we do, I'd like to take a moment and do an example problem based on the material that we covered on Tuesday. Because days of the week are still hard for some reason. Alrighty, so for the following, acid-base equilibria or I should say equilibrium, because it's singular. Identify the acid, base, conjugate acid, and conjugate base. All right, so, and the acid-base reaction is the following. Let me see. So sulfuric acid is reacting with a molecule called sodium methoxide. You don't need to know how to name that. It's an organic molecule, and they produce sodium sulfate and methanol. All right, so we are asked to determine the acid, to identify the acid, the base, the conjugate acid, and the conjugate base. Now, by way of reminder, actually, let me get my color palette here. There we go. So the important thing to keep in mind for this reaction, or so for this problem, is that when they ask you for the acid and the base, this is for the forward reaction. And the thing to remember is the conjugate acid and the conjugate base, these are the acids and bases in the reverse reaction. All right, so what makes something a conjugate acid is it is the acid reacting in the reverse reaction. What makes something a conjugate base is it is reacting as a base in the reverse reaction. So acid base, forward, conjugates for the reverse. All right, so first off, we need to identify our acid and base. Now, the way you do this, you'll recall that the definition of an acid, the Bronsted-Lowry definition, is the one that I'm going to use. It's probably not probably, it is the easiest to use in this context. The Arrhenius definition allows us to identify an acid and base based on what they produce in water. But this isn't a reaction with water. This is a reaction between compounds, chemicals, making other chemicals. So when you are looking at a reaction that isn't with a molecule of water, the Bronsted-Lowry definition is the way to go. And the definition of an acid, according to Bronsted-Lowry, is the definition is it is a proton donor. So if you're losing H+, that makes you an acid. And the Bronsted-Lowry definition of a base is it is a proton acceptor. So if you're gaining H+ throughout the course of the reaction, then you are a base. And so the best way to go about this is, in an acid-base reaction, the only thing that changes is an H+ changes hands. So you should look, so for example, if you're wondering, is this an acid or a base? Try to find a structure similar to this on the product side. And you can find specifically the SO4 chunk of this molecule is present here and here. And ask yourself, how has it changed? Well, has it gained H's? Has it lost H's? And it's clearly lost H's going from the reactant side to the product side. So since H2SO4 has donated hydrogens, that makes this the acid. Now let's identify our other piece. And again, we're evaluating what this turns into right here. And actually, I'm just realizing that my reaction is not balanced. Need to put a 2 here and a 2 here to properly balance it. So here we can see that OCH3 becomes HOCH3. We've picked up this chunk of the molecule has gained a hydrogen through the reaction, so it is a proton acceptor, making this the base. All right, so we've identified our acid, we've identified our base. Now we need to identify our conjugate acid and conjugate base. One interesting thing when you evaluate, sorry, I wrote this in the wrong layer. There we go. Okay, sorry about that. Let me shape this up. This is the base. All right. Now, when you're evaluating the reverse reaction, so now we're looking at the reverse. When you start with methanol and you go in the reverse direction, you have lost a hydrogen moving in this direction, right? You have an H on that O, but that H is gone. It's been replaced by a sodium. So in the reverse reaction, methanol is the acid, and the name of an acid for the reverse reaction is a conjugate acid. All right, if we apply this type of analysis to sodium sulfate has gained 2 H's going from the product side to the reactant side in the reverse reaction. Since it has accepted hydrogens, that makes it a base. So this, because it's the base of the reverse reaction, we label it the conjugate base. Now, if you're noticing a pattern, you're like, wait a minute, the acid becomes a conjugate base, the base becomes a conjugate acid. If you're wondering, is that always going to be the case? The answer is yes. It 100% is. The acid always becomes the conjugate base, and the same is true, or the flip is true of the base. The base for the forward reaction always becomes the conjugate acid. So they will always reverse their roles in the reverse reaction, just like a mirror image. It's identical but opposite, right? Flipped, that's what happens. Acid becomes conjugate base, base becomes conjugate acid, and vice versa. All right, so this is an example based on the topics and materials we were covering yesterday, or not yesterday, Tuesday. But now let's go ahead and dive into some new material. All right. Now, admittedly, when I began a discussion of this chapter, when I said, okay, this chapter is about acids and bases, acid is a word that evokes a reaction. It's been kind of enshrined in our popular culture, right? Acid is the xenomorph's blood from Alien, right? Eating through the hull of the ship. Acid is the thing that like burns Two-Face's face. Acid is the vat of acid. The Joker falls into it and goes from a normal guy to being insane and, homicidal maniac. So it's like acid is a word that's charged, right? Acid is a word that's scary. And it's true that there are a lot of acids that can burn you. But it's not true of every acid. As we've seen, water can act as an acid. We're drinking it. We're breathing it out. As I speak, I am exhaling water vapor with my words. So, someone asks you, what did you learn in chemistry class? You can say, I learned I'm a meat-colored skeleton exhaling acid every moment of the day. That sounds terrifying. But it's true. Water's an acid. But it's not a harmful acid, right? It's not a strong acid. Now, we have a way, as chemists, as scientists, of communicating how strong an acid is, rating how strong an acid is. And we actually use a chemical reaction called acid ionization. With water. Or I should say in water. And we use this reaction as a way of rating, as a way of measuring how strong an acid is. Well, what is an acid ionization in water? There's a reaction. I'm just going to write this acid generically as HA, so it can be any acid, which is in the aqueous phase. It will react with water, H2O, liquid, and the products will be hydronium, because the acid donates a hydrogen to water. Water becomes hydronium. And once the acid donates H+, what's left over is the rest of the molecule minus an H and minus a positive charge. Remember, an acid is a H+ donor, so it's given away a positive charge. If it's lost a positive charge, that means there is a negative charge left behind. All right, so this is the equation. This is the equilibrium for the ionization of acid, just a generic acid in water. All right, and we can write an equilibrium constant for this reaction. All right. Because it's a reversible reaction. We can write KEQ. Now, then this, we're not going to label KEQ. We're going to label this KA because it is the equilibrium constant for the acid ionization in water. So it gets a special little label. And just like every equilibrium, it equals the concentration of products over the concentration of reactants. So we have hydronium, we have A minus, the conjugate base, over, so those are our products, over the molarity of our reactants, which is just going to be HA. Remember, you never include solids or liquids in the equilibrium constant. They're a no-go because they have a constant concentration. That concentration isn't changing. So only aqueous media and gaseous substitutes make it into an equilibrium constant. All right. All right, now, everything that we learned about equilibrium constants applies here. Remember, we're dealing here with products, a ratio of products over reactants. All right. And so what determines how strong an acid is essentially the number, the size of the acid ionization constant. All right, strong acids have large Kas. Weak acids have small Kas. All right, and think about what this means. A large Ka means that you have more products. So the acid, if you have more products, that means the acid is dropping its proton onto water. It's reacting aggressively. A small Ka means there's more reactions. That means the acid is hanging on to its hydrogen. It's not very good at giving it away, at protonating something, which makes it a weak acid. It's not very aggressive. It's not very reactive. So that's why we look at Kas, because the number itself can tell us something about the strength of the acid, whether it's aggressively reacting, whether it's mildly reacting, or maybe not reacting at all. All right. Strong acids, the dangerous kind, have large Kas because they produce a lot of hydronium. All right. That is what strong acids are in the business of making, a lot of H3O+. All right. Now, this is interesting. All right. So there's a factor, there's a quantity called percent ionization. All right. And percent ionization tells you the percentage of the acid that reacts to produce hydronium. All right, so for example, if you had an acid so an acid with a 10% ionization, what that means is of the original amount of acid that you started with. So let's say you had a solution of 1.00 molar of this acid, 10% ionization. That means 10% of your original amount of acid has ionized into H3O+. So that means, for example, that if 10% of this ionizes, you will have a 0.00 molar solution of hydronium, and that's 10% that it lost, so you'll have a 0.900 molar solution of HA, because 10% of it ionizes away. Start with 1 molar, 10% ionizes, you're left with 0.9 molar HA and 0.1 molar H3O+. All right? Now you can actually use the percent ionization of an acid to calculate the value of your acid ionization constant, of that equilibrium constant. And here's how you'd go about doing this calculation. Let's see, I'm going to rearrange this. Just give it 1 sec. I want that there. I want this here. Actually, it looks like I'm going to need to trim this down a little bit. All right. The types of fun rearranging things that you cannot do with a traditional whiteboard. I'm definitely going to miss the digital canvas once regular instruction returns. Okay. So let's take a look here. Calculate the acid ionization constant. I'm just going to say calculate Ka, save some space. For a 0.100 molar solution of HA, if HA has a percent ionization, of 25%. All right. So, first off, let's identify what we're trying to find here. We're trying to find Ka, and Ka, based on the above equation, is equal to the concentration of hydronium times the concentration of the conjugate base over the concentration of HA. All right, so we need to find three things to do this calculation. We need concentration of hydronium, concentration of our conjugate base, and the concentration of HA. We can do this with our percent ionization. So let's think about what our percent ionization means. All right, percent ionization means that 25% or 1/4 of HA reacts. So we lose 1/4 of it, all right? 1/4 of, and remember, of is a word that means multiplied, right? So that to calculate how much of HA reacts away, that's 1/4 times, shoot. Here, hang on 1 second. Thought I opened a new layer. Here we go. That's 1/4 times our initial concentration. If you multiply 0.25 times 0.1, or if you take 0.1 divided by 4, either way, this will come out to be 0.0250 molar. And this is the amount of HA that reacts. So if you want to know how much HA is left, if you want to know the concentration of HA that's left, you got to take the initial amount and subtract 0.0250 molar. All right, HA is 0.075 molar. And our last sig fig, you'll notice, is right here. So we only have 2 sig figs for HA. All right, that is the amount that we will be plugging in right there. All right. So that's our concentration of HA. But now, what about the concentration of hydronium? Well, this is also going to come from the amount of HA that reacts away, because 1 mole of HA produces 1 mole of hydronium. So if we produced, if 0.0250 molar of HA reacts, that means that our concentration of hydronium is 0.0250 molar. And you'll notice the same is true for a conjugate base. 1 mole of HA produces 1 mole of A minus. So our concentration of A minus is also equal to 0.0250 molar. We've got both pieces of our numerator. We are ready to calculate our answer. Our concentration of hydronium is 0.0250. We don't include units for equilibrium constant, so we can just plug the numbers straight in, then divided by 0.075. Our numerator, both numbers in our numerator have 3 sig figs. Our denominator, however, only has 2, so that is going to limit our answer to 2. Now my calculator is telling me that the answer is 0.008333 forever, but we can only have 2 sig figs. So 0.0083 is the acid ionization constant for an acid whose concentration is 0.100 and has a percent ionization 25%. All right, let's do another example like this. Now that we've kind of seen how to go about it, let's get another rep in. All right. What is the Ka of a 1.00 molar solution of an acid HA with a percent ionization of 6.0%. All right, so once again, we have Ka here. We know that's what we're trying to find. And we need the concentration of hydronium, our conjugate base, and HA. Now, the percent ionization tells us that what HA loses. All right, so we need to figure out how much does HA lose. 1.00 molar times 6%, right? That's 6 over 100. So HA is going to lose 0.0600 molar. All right, that's how much it loses. So the HA left is our initial concentration minus what it's lost. So our concentration of HA is 0.94. We've got to have our last sig fig in the second decimal place. Now the amount that it loses here is also important because this is also it also tells us the amount of hydronium made and the amount of conjugate base made. So our concentration of hydronium is 0.0600 molar, and our concentration of conjugate base is 0.0600 molar. So we actually now have all three pieces to calculate the acid ionization constant. Right, Ka is the concentration of hydronium times the concentration of a minus conjugate base over the remaining concentration of our acid. So this is 0.0600 times 0.0600 over 0.94. Which my calculator is telling me that the value is 0.00382. I can stop there because I have to round to 2 sig figs and 2 rounds down. So my final answer, the value of Ka is 0.0038. Is the acid ionization constant for HA in this problem. One of the things that I want to point out is if you flash back and look at our previous problem, let's see. There we go. Oh wait, no, that's there it is. We actually have a larger value for the percent ionization for the ionization with the previous example. Okay, so here. Sorry, let's just throw this on a new slide. When we had an acid with a 25% ionization, we had a Ka of 0.0083. When we had a 6.0% ionization, our Ka has a value of 0.0038. Funny symmetry there, purely coincidental. Notice that a larger percent ionization gave us a larger value for Ka. That's because this acid is stronger. It's stronger because it's producing more hydronium. It has a higher percent ionization, and the Ka reflects that. The lower percent ionization gave us a smaller value for Ka, which tells us that this acid is weaker, so it all connects together. It all ties together. All right. So that's our introduction to Ka. We're not done with it. We'll come back to it before the chapter is over. But we're going to move on temporarily and discuss a new topic known as a neutralization reaction. So acid-base, neutralization. All right, acid-base neutralizations. All right. If you look up in your book, acid-base neutralization, it'll tell you that it is a reaction between an acid and a base that produces salt and water. I'm going to be a tad more specific. A neutralization reaction is a reaction between an acid and a metal hydroxide base that will produce water plus a salt. All right, first off, generically, the acid is the acid is HA. The metal hydroxide, that's just a metal cation. Sodium, potassium, any metal, really. I don't know what phase it is. And it produces water, H2O, plus, now what is this salt situation? A salt is just a generic term in chemistry. That means it could be any ionic compound. All right, any ionic compound. All right. And specifically, if you're wondering, okay, it can be any ionic compound, what ionic compound will it be? It will be the ionic compound that forms when the metal cation combines with the conjugate base, which is an anion. This also, we don't know the phase of this guy, but the metal, the cation for the salt comes from your metal hydroxide, and the anion for the salt is the conjugate base after the acid has removed its proton. One quick note, if you're wondering why did I put question marks here and here for the phase, the reason why is you have to use solubility rules. To figure out the phase, right? You've got two ionic compounds. Some of them will be soluble, some of them will be insoluble, and you have to apply the solubility rules. So again, that's another reason to have the solubility rules either memorized or on your exam sheet, so you can reference them to get these phases correct. All right. Now, the reason why, so chemistry professors love neutralization reactions. They love them. And the reason why we love them is because I don't have to tell you the products to ask you to balance the chemical equation. I can just give you the reactants and say, write a balanced chemical equation. Because they always follow this pattern. Let me show you what I mean. All right, so for example, write a balanced neutralization reaction for the reaction between HClO2. This is chlorous acid. I don't believe we've learned how to name it, so you don't have to worry about it. And sodium hydroxide. This is aqueous because you'll remember sodium is always soluble, so anytime it's paired with anything, it'll be in the aqueous phase. Now, let's figure out how to write a balanced chemical equation. All right, so starts with, we know the reactant side. All right, but what are the products going to be? Now, here's the beautiful thing. Acid-base neutralizations will always make water. So you can always write H2O as a liquid. You're halfway there. Next, we got to figure out this metal hydroxide part. All right, now the metal is sodium. So sodium metal is Na with a positive charge, right? Now, what about A minus? The conjugate base is the chunk of the acid after it donates away its proton. All right, so it's going to be ClO2, and we only have one H, which means we're going to have a charge of -1 left behind once you donate that proton. Now, these two are going to combine in a 1-to-1 ratio because you have a charge of +1 on sodium, a charge of -1 on chlorite. So these will combine as just NaClO2. All right. On our reactant side, we have one hydrogen from the acid, a second hydrogen from sodium hydroxide. We have one chlorine. We have 2 oxygen from the acid plus 1 oxygen from sodium hydroxide. And then we have 1 sodium atom. Let's look at the product side. We have 2 hydrogen, right? 1 chlorine, 1 plus 2 oxygen, right? 1 from water, 1 from sodium chlorite, and 1 sodium. All right. Looks like this thing's balanced. So we don't actually have to do anything beyond this step. Let's do another example. I'm just going to scoot this up to give me a little more space here. All right. Let's see. Let's do, oh wait. Exact same problem. But we're going to change. Whoa. It's not my intended result. How about this? There we go. We're going to write a balanced chemical equation for the neutralization reaction between hydrobromic acid and magnesium hydroxide, which is a solid. Because magnesium is, hydroxide is usually insoluble. So let's write out our balanced chemical equation. HBr plus magnesium hydroxide reacts to produce. Now again, beautiful thing is you will always make water in these reactions. H2O liquid, guaranteed. Now we have to figure out that salt. All right, now the metal is magnesium, which when you figure out its charge from the periodic table, it's a charge of +2. The conjugate base, you lose one H. It'll leave behind a charge of -1. So it's bromide. Now, when you look at these charges, we're going to need 2 negative charges to balance with our charge of +2. So we need 2 bromides to every 1 magnesium. So the salt that we're going to make is MgBr2. Bromine is, according to the solubility rules, usually soluble. It's insoluble with lead 2, mercury 1, and silver. Magnesium's not on that list, so this is in the aqueous phase. All right, now we have to balance this thing, or see if it needs to be balanced. Let's see if we get lucky like we did last time. So we have hydrogen, bromine, magnesium, and oxygen on both sides of this equation. Oops. Oh, here, hang on. Sorry, I started writing this in the wrong layer. It's not a problem that shows up with traditional whiteboards. Oh, but I could also do this. There we go. So hydrogen, there's 1 hydrogen in HBr plus 2, right, in magnesium hydroxide, 1 bromine, 1 magnesium, and then 2 oxygen from magnesium hydroxide. On the product side, we have 2 hydrogens, 2 bromines, 1 magnesium, 1 oxygen. You always go for the path of least resistance on these things. So I can see here that I've got 2 bromine on my product side, 1 on my reactant side, so I need to multiply HBr by 2. This is going to change my hydrogen count and my bromine count simultaneously. Now I have 2 plus 2 hydrogens and then 2 bromines. Another one that's an easy fix is oxygen. Right, I've got 1 on the product side, 2 on the reactant side, so I need to multiply H2O by 2. This is going to change oxygen and hydrogen simultaneously, and as luck would have it, sorry, that's not a 4, it should be a 2. Balance the entire thing in one foul swoop. Now we have 4 H's on both sides, 2 bromines, 1 magnesium, 2 oxygen. So we're good. This is the balanced neutralization reaction between hydrobromic acid and magnesium hydroxide. All right, now you got to pause for a minute and ask yourself, what's the point of balancing chemical equations in the first place? There's only one reason why you balance a chemical equation, and that is to do stoichiometry. So this will allow us to solve problems like the following. Um, 25.0 milliliters of 0.100 of a 0.100 molar solution of sulfuric acid are mixed with 25.0 milliliters of 0.100 molar barium hydroxide. All right. Part A. Write a balanced chemical equation for this reaction. Part B. Determine the theoretical yield. Oh, wait, sorry, I messed this up. This should be 35, not 25. The theoretical yield of water in grams. Part C. What was the actual yield of water in grams if the percent yield was 98.5%. All right. We're taking off a big bite. This is a lot of things all at once, but this is the caliber of problem you can expect at this point in the semester. We're near the end. everything's coming to fruition. This is a great example of what you should expect out of a final exam problem. All right, so let's dive in. First, let's do part one. Let's balance this reaction. I'm actually going to clear a little bit of room. All right. So first, let's balance this thing. We've got, oh, well, okay. We actually need to pull back and do some acid nomenclature. Here we're dealing with an ic acid. That means that the conjugate base, the anion on which this acid structure is based, is sulfate. Sulfate is a polyatomic ion with a charge of -2. So that means sulfuric acid is H2SO4 plus barium hydroxide. Barium has a charge of +2. Hydroxide has a charge of -1. So this is going to be BaOH2. Now the products here of any neutralization reaction, water, salt, right? So we're going to put H2O, it's a liquid, plus salt. Now the salt is based off of the conjugate base, sulfate, and barium. They have the same equal and opposite charges, which means they combine in a 1-to-1 ratio. So this is just going to be BaSO4. And actually, let's not worry about the phase symbols for this reaction. All right, so let's see if this thing is balanced. We have hydrogen, sulfur, oxygen, and barium on both sides of this reaction. We have 2 hydrogen from sulfuric acid plus 2 hydrogen from barium hydroxide, 1 sulfur atom, 4 oxygens from sulfate, 2 from hydroxide, and 1 barium. On our product side, we have 2 hydrogens, 1 sulfur, 1 oxygen from water, plus 4 from barium sulfate, and 1 barium. All right, again, go for the easiest possible thing that jumps out to you. The one that jumps out to me is hydrogen. We have 4 on the reactant side, 2 on the product side, so we need to multiply water by 2. This will alter both hydrogen and oxygen simultaneously. Now we have 4 hydrogen, and we have 2 plus 4. All right. And this is our balanced chemical equation. Gonna move that up there. Because we're gonna need it. Call that good. All right, now let's look at the other parts to this problem. Okay, we need to determine the theoretical yield of water. That's part B. Oops. And you'll notice that we're given initial quantities of sulfuric acid and we're given initial quantities of barium hydroxide. This means we're dealing with a limiting reactant scenario. If we had just been given one, then the assumption is the other one is in excess. We calculate it, but we don't know which one is going to determine our theoretical yield because we don't know which one is limiting. So we need to calculate the theoretical yield of water based on both quantities, whichever is, and compare them. Whichever one is smaller, that is the one that we're going to go for. Now, if you're wondering, if you'd given me grams, Josh, I could do this, but again, the molarity thing still weirds me out. Remember, the equation for molarity is equal to moles over volume in liters. That means if you are given both molarity and your volume in liters, you can solve for moles. You can do this if you multiply both sides of this equation by liters. Liters cancels the denominator, and you get a new equation. The moles dissolved in solution are equal to the molarity of that solution times its volume in liters. We're going to need to convert both of these volumes from milliliters to liters then if we're going to use this equation. So let's just go ahead and knock that out of the way. We want milliliters to cancel. 1 liter is 1,000 milliliters. So 25 milliliters will be 0.0250 liters. Likewise, $35.0 milliliters converts to 0.0350 liters. So those are our two volumes converted to liters in one fell swoop. All right. With that out of the way, we can begin our calculation. So we start with 0.100 molar sulfuric acid. Remember, molarity is moles over liters. Whenever I'm doing a mathematical calculation, I always split my molarity into its numerator and denominator because it helps me visualize it better. When we multiply this by our volume in liters, you can see that liters cancel liters. Next, we need to convert from moles of sulfuric acid to moles of water. And this is a 1:2 ratio. Moles of sulfuric acid cancel. Lastly, we need to calculate, convert moles of water to grams of water. We've calculated the molecular mass of water before, so When you do, you'll realize it's 18.016. And here, moles of water cancel moles. And now we crunch our numbers. We have 0.1 times 0.25 times 2 times 18.016. All right, this comes out to be 0.9008 grams. We can only keep 3 sig figs. So this 8 would round up. But we don't know if that's our theoretical yield. Let's do the other calculation first before we go any further. So let's calculate this based on the initial amount of barium hydroxide, which is 0.100 molar. Times 0.0350 liters. Now liters cancel liters. Times, now we need to convert from moles of barium hydroxide to moles of water. And much like before, we can see that this is a 1:2 molar ratio. Moles of barium hydroxide cancel. And we multiply this by our molecular mass of water. So that moles of water cancel, and we're left with grams. So let's crunch these numbers. 0.1 times 0.0350 times 2 times 18.016. This comes out to be 0.1261 grams. But this number is clearly bigger, so it is not our theoretical yield, which means that our first value is, we got to round to 3 sig figs, so this is 0.901 grams of water. This is our theoretical yield. All right. That is part B. We have one piece left with part C. Okay. Part C, let's see. What is the actual yield of water in grams if the percent yield is 98.5? So here to solve this part of the problem, oops. No, not that part. There we go. We got to remember that percent yield is equal to actual over theoretical times 100. And we've been given percent We calculated theoretical in part B. Obviously, we know what 100 is. So 98.5 is equal to our actual yield, whatever that is, over our theoretical, which is 0.901 grams times 100. Multiply both sides of this equation by 0.901 grams over 100. 901 grams over 100. This gives us our actual yield of let's see. Let's, actually calculate that. We have 0.901 times 98.5 divided by 100. Gives us an actual yield of it's the ugliest 8 I've ever drawn, 887 grams. That is an actual yield. I wanted to do a problem like that to kind of jog our memories. Stoichiometry we got introduced a while ago, but it's always present and it's always relevant to what we're doing in this course. So I just wanted to kind of do another example, bring it into the forefront, look at a limiting reactant problem in the context of acid-base chemistry. All right, let's see. Okay, I'm looking at what comes next. And I think I'm going to call this here the next kind of, well, let's leave off lecture with a question. So I want to set up Tuesday's lecture. I want to set it up with a question posed to you. All right, so if I asked you, is water an acid or base? If I asked you that, hopefully you'd respond and you'd say, Josh, words, acids, bases, it's not an identity. It depends upon how water is reacting, but it depends upon how it's behaving in relation to the other species in a reaction. Water could be an acid in one reaction, it could be a base in another reaction. It just depends on the context. To which I'd say, very good. You didn't fall into my trap. So if water can be an acid, and water can be a base, can you write a balanced chemical equation for the reaction between these two molecules. Let me give you a couple hints. There's going to be two products. I call this product 1, which is aqueous. I'm going to call this product 2, which is also aqueous. And I'm going to give you one more hint. In this reaction, this molecule is an acid, and this molecule is a base. Can you write the balanced chemical equation for this reaction? Give it a try over the weekend. We'll come back, start with this next Tuesday. Later, dudes.